All right, here's our first truss example. This is 6.1 in your textbook. For trusses, you typically start at the area of the least unknowns. While looking at the truss, I discovered that C is the joint with least unknowns because it has only two unknowns in there. So I'm going to start at joint C. Typically, when I solve for method of joints, I normally assume every single force is in tension. After you write the free body diagram of the joint, you have to use the equilibrium equations Fx is equals 0 and Fy equals 0. Soon after this, go ahead and plug in the forces in this joint and solve for the unknowns. All right, we're back. I wrote down a little bit of extra stuff because I didn't feel like doing it all on camera. But as you can see, I originally wrote my joint in tension for all parts, but you cannot have two negatives in this because it won't equal equilibrium. So I had to actually switch force CD into compression so it can equal out from the compression at 20 kilonewtons. So then after that, I plugged in my equilibrium equation, negative 20 plus CD equals 0. So member CD equals 20 kilonewtons. Okay, since we started at C, we also have to move in the process of least unknowns. So going down the truss, I would move to D because I only have two unknowns at D, unlike B where I have the support forces as well as A where I also have the support forces. Also, by the way, in the little corner in the top left, I wrote the directions of compressions and tension. Tension is always pulling away from the joint, while compression is always pulling towards the joint. Therefore, you can see it at joint C, where tension, CD, is pulling away from the joint, and compression, CD, is is going towards the joint. I started joint D already by drawing first. This is very important. Always draw a free body diagram first because that's the key to success. So once I did that, I labeled my forces, DA and BD, which I had to break up into components because it is a diagonal force that is, and it has an X and Y component. And I had to do some trig magic using this triangle right in this little area. It's 2 and 1.5. It's kind of hard to see. So now that I have a least unknown in the equation Fy, I'm going to solve for dB so I can make my truss life easier. Just give me 1 second, I'm typing it in the calculator. So I got dB equals 33.33. And don't forget units. For this case, we're using kilonewtons, so Kn. All right, now since we have dB, we can move to the Fx and solve for that. dA plus 33.33, 2 over 2.5, and you just do some algebra and set dA is equal to 26.664. And now that we solve for that, we can make our lives easier and go ahead and solve for the support forces at A, and then or support forces at B. It's either one of our choices, but I'm going to start at joint A. So here is joint A. Since joint A only has one Y force, that Y force is automatically going to be 0 because it cannot have a force or will not be in equilibrium. Also, I had to redraw joint D because I assumed dA was in tension, which was incorrect because dB, which is the only tension force acting on this object, has a tension in the x direction. Therefore, dA has to have a compression to cancel that out and be in equilibrium. So, setting this in equilibrium, I wouldn't have to do much work. All I have to do is say Fx equals 0 and label my two Fx forces, dA and RAX, and set them equal to each other, which would be dA equals RAX, which is equal to 26.664, because they're in equilibrium, they must balance out. All right, thank you for watching the video for trusses. We solved our first truss. Good luck on studying. All right, guys, I actually forgot the 10 kilonewton force at joint D, so we're gonna have to draw that here real quick. Acts like this. So if it acts like that, it's going in the positive x direction, so I would just have to add plus 10 to my dA, because it is plus 10 to the force, so it would actually be 36 kilonewtons. And this would also be 36 kilonewtons. All right, well, thanks for watching the video, guys.